Can you handle each of those individually? Yeah. Not bad at all, right? Antiderivative of 1 would be x. So I'm going to have 1/2 here. I'll have x. And then what is the antiderivative of cosine 2x? Be careful. 1/2 sine 2x dx. No, not dx, plus c. Oops. And you can multiply the half through now, right? And we'd be done. We'd be done. Pretty clean, right? So this even power is not so bad. Be careful what you wish for.
So we can, like, if it was like cosine to the 6th power.
Oh, I'm so glad you said that. Now you're going to see this is, yeah, here we go. Yeah, this is a lot of work. This is going to be a lot of work. Well, every time I see this, I think about myself doing this, like when I was a student. And this was an eye-opener to see the amount of work required to do this problem. It kind of changes your perspective on the magnitude of things. Like, you know how you're like, oh, like in Cal 1, you did these problems that took up a lot of space on a page, you know? Like, you do a problem like this, you're like, whoa, okay, so this is how long they can get. Like, it's longer than you thought it could be. Yeah, so because this is even, you can't peel one off, right? Can't? The best you can do is rewrite this as cosine squared x cubed dx. Right? And then you can rewrite cosine squared x using the power reducing formula, 1/2 times 1, right, plus cosine 2x. Let's put a star next to this problem. I would never give you a problem like this on the test. That in no way means to turn off your attention. Stop paying attention, because this is a classic problem. All right, every Cal 2 student should suffer through this problem. All right, so you with me up to that point? Okay, now what we're going to do, dx. What we're going to do now is we're going to apply the cubed. So I'm going to cube the half and then cube this. So this is going to become 1/2, 1/2, 1/2. That's 1/8, yes? Take it out of the integral. And then in here, I still need to do 1 plus cosine 2x, but I need to cube that dx. We still at this point cannot take an antiderivative, because this thing is cubed, right? When that wasn't there, we were fine. We could do them each individually. But because it's cubed, we have to keep going.
So where did the 1/8 come from?
When you cube a product, this is this times this, you can cube each one. So 1/2 times 1/2 times 1/2 just took it out. Okay, so guess what we get to do with that now? Expand it. We do 1 plus cosine 2x times 1 plus cosine 2x times 1 plus cosine 2x. Why can we not do a u substitution right now? Why can't we do like u is cosine 2x? There's no sign anywhere, right? You can't do there's no derivative of it there. So here goes. This is now going to become, all right, I'm giving myself plenty of room this way, okay? I have 1/8 integral. So if you cube this, yes?
You can't use the shortcut sum of cubes.
Sum of cubes. This is not a sum of cubes. It would have to be this cube plus this cubed, yeah. So we just have to expand it. Now, I don't feel like doing it all, but I'm trusting you could. Yay or nay? No, should I not? Okay, I won't trust you can do it. So I'll do it right here real quick. Let's do it this way. Maybe this will help. I in no way am making a substitution here. Now I better just do it. Shit. Okay, 1 plus cosine 2x times 1 plus cosine 2x times 1 plus cosine 2x. Okay, The way I like to do cubes is I like to actually start with these two first and leave this one out here. All right, this is just algebra, so I'm moving fast. FOIL here, collect like terms. It would be 1 plus what? 2 cosine of 2x plus, be real careful, what here? Cosine squared of 2x. Okay, that's what we get when we do that first one, right? Okay, now we have to come through and multiply by this through, right? And then that one through. So we get 1 plus 2 cosine 2x plus cosine squared 2x plus cosine 2x plus 2 cosine squared 2x plus cosine cubed 2x. Did I do that too fast? Or are we good? That's just... Yes? Collect like terms. 1 plus... How many 2 cosine 2x's do we have? How many cosine 2x's do we have? 3 of them, right? 2 of them, 1 of them. So we have 3 cosine 2x's. How many cosine squared 2x's do we have? 3 of them. 3 cosine squared 2x. And how many cosine cubed 2x's do we have? 1. Cosine cubed 2x. Yeah, I have the one out front. Okay, you ready? You're not going to like this. You're going to like it. But you don't know you like it yet. Okay, 1 plus 3. If it seems like I'm getting any sort of pleasure out of this, like seeing the suffering that you're going to endure, it's not pleasure. It's elation. I think is more. No. No. It's teaching this class never gets old for me because this is like a journey. Like you were on a journey. Cal 2 is a journey, and I enjoy seeing people have to go through this journey because you really kind of, you have to grow up in this class. Like you have to mathematically grow up and be mature. There's no way around it. And so I like to see that development. And a problem like this really kind of, whoa. So that's the expansion. Ready? Can you find the antiderivative of that? Okay, good. We're happy about that. This one? Yeah. What's the antiderivative of cosine 2x? Like there's like a half sine 2x or something? So far, so good. Uh-oh. Cosine squared 2x. How do we handle cosine squared? We have to use this, right? So we're going to have to do this, but didn't we start the problem by doing this? Okay, so we're going to have to do this again. Okay, and then cosine cubed. That's an odd. So I can peel a cosine off and do what I did before we started this problem. You see that? So I've got a lot of work to do here. All right, let's keep going. I think we had pi x's in there. All right, now 1/8. I'm going to keep that 1/8 out here. Antiderivative of this is x. Okay, antiderivative of this will be 3 over 2 sine 2x, right? And then from here on, I've got work to do, right? So I'm going to say, done with that. Those are the first two. Plus 1/8 integral. Actually, you know what? I'm going to make it 3/8 cosine squared 2x dx plus 1/8 integral cosine cubed 2x dx. All right, do you all follow what I did on that step? Everyone good? This and this I did, the antiderivatives, I kept the 1/8 out in front. And then that 1/8 I put in front of this one, and I'm going to set up its own integral. And then 1/8 in front of that one, set up its own integral, right? The reason why I'm doing them separately is because this one's a different technique than this one, right? Okay. Yes?
Just to clarify, we don't peel apart even the even powers because of the formula?
We don't peel the evens apart.
For example, on cosine cubed, like we can peel apart one cosine cubed,
Mhm.
but on cosine squared, we don't peel apart.
Do you see why?
I imagine it's because
Let's just look at that. Let's say I took, I'm going to look at this one right now real quick. If I take cosine 2x times cosine 2x, that's cosine squared, right? This right here is the derivative of sine in some fashion, right? So that means if I could rewrite this in terms of sine, I'd be in business. The problem is you don't have a way of rewriting this with a sine. This would have to be cosine squared. Then you could rewrite it as 1 minus sine squared. But because it's just cosine, you can't just switch it to sine. Does that make sense? So peeling off on an even power isn't going to work. Here, it does, because now with the cubed, if I do cubed here, right, then that becomes squared when I peel one off. Then I rewrite that as 1 minus sine squared. And then I've got my u and my du. All right. Let's continue. This right here is just going to keep coming down with us, all right? All right, so here plus 3/8, nope, 3/8 integral. Now, how do we do this? Cosine squared of, be careful, cosine squared of 2x should be 1/2, parenthesis, 1 plus, drum roll, cosine 4x. Why is it 4x? Because the formula says, if you want to change cosine squared of x to something, right, it's going to become 1/2, 1 plus cosine of double the x. So if that's already 2x, it now becomes 4x. If that was 8x, that becomes 16x. It doubles the angle. All right. Plus 1/8 integral. Say it again.
Can you split that? Can you split that as a cosine squared and just rewrite that as 1/2 1 plus cosine 4x times cosine?
So you're saying split this into cosine squared times cosine, right? And then rewrite the cosine squared using this one?
Right, just like that.
Would not want to use this one. The reason why is because, let me just write down what you were suggesting. If we do cosine squared 2x times cosine 2x, that's what you're saying, right? Split it. If we rewrite this, right, using the bottom formula, what's the argument of the cosine function going to be? What's the thing inside of it going to be? Is it going to be 2x or 4x? 4x, right? So you'll have a cosine 4x here. And this is not the derivative of cosine of 4x, right? So we need this piece to be rewritten in terms of sine, and so we're going to go back up to the Pythagorean. So this problem right here is odd. When we see odd, Pythagorean. Okay? So let me see if I can do this one. Cosine squared 2x times cosine 2x dx plus 1/8, and I'm rewriting this as what? 1 minus sine squared what? 2x cosine 2x dx. Yeah.
not like that.
Yeah.
Wait, it's fine.
Okay, I'm going to keep it going here. I don't want to erase that. I have, so far, equals, I have 1/8 x. That was, I just erased this. This was 1/8 x. I'm going to distribute that through. That should be plus 3/16 sine 2x. That was these first two terms with the 1/8 distributed, right? All right, let's talk about the next piece, this right here. Okay, I'm going to bring this 1/2 out. So I'm going to have what out front? 3/16. And then let's go ahead and take the antiderivative. Okay, the 1/2 came out. Antiderivative of 1. X plus the antiderivative of cosine of 4x. Christopher. G. antiderivative cosine 4x. Right, that's where we are? 1/4 sine of 4x, okay? So now we've taken care of this one, right? Taken care of this one. We still need to work on this one, right? So I'm just going to leave this as an integral. All right, that's where we are. And Jacob? Jacob? Whew, good. Where's Jacob? Okay, Jacob. How are we going to do this one? What technique will we use to go after this now? So, power reducing, how did we get to this? Didn't we started off with odd power of cosine, didn't we? Once we did odd power, we rewrote it this way, and that's what we started this whole idea with. When we get, the whole class, right, started with the idea of trig functions to an odd power. So, once we're here, do we see something in its derivative? Right, like a basic u sub. Okay, so what would the u be? Sine 2x. Sine 2x. Derivative of that is going to be 2 cosine 2x, which we don't have the 2, right? So we just hit it with a half dx. So all of this stays the same. And then this becomes plus 1/8 integral 1 minus what? U squared du. And then we also have a half, right? So let's just bring that half out here. We're close, okay? We're close. We're almost there. So what's the constant in front? 1/16. Antiderivative time. Antiderivative of 1 is u. And what is u? Sine 2x. Minus antiderivative of u squared. 1/3 u cubed. But what was u? Sine 2x cubed. So this is going to be u minus 1/3 u cubed. And then plus c. And then all that stuff out front. And we're still not quite done. I'm going to take this stuff out front. I'm going to distribute this constant through, and I'm going to distribute this constant through this one. And at that point, we will almost be done. We have 1/8 x plus 3/16 sine 2x plus 3/16 x plus 3/64 sine 4x. Oh, shit, I just erased what I needed. Didn't I? I just did, didn't I? Okay, so we, 1/2, it was 1/16. So it's 1/16 sine 2x, right?
Minus 1/3 sine cubed.
Minus what?
1/16 minus 1/3 sine cubed 2x.
1/16, and it was 1/3, right?
Oh, so then it's
1/48? 1/48 sine cubed 2x. That's not cubed, that's squared. Plus c. We're not going to factor. We're just going to collect like terms. We're just going to collect like terms, because that's a 1/8 x and that's a 3/16 x, right? And then in terms of sine 2x's, these two are both sine 2x's, right? Everything else is different. So what's 1/8 x plus 3/16 x? 5/16 x. 5/16 x. Then how many sine 2x's do I have? 4/16, so 1/4. 1/4 sine 2x. And then we have 3/64 sine 4x and minus 1/48 sine cubed 2x plus c. That is the antiderivative of cosine to the 6th x.
How many times have you done this problem?
I'm going to guess 50?
Every semester, huh?
Yeah, probably every semester in multiple classes.
Oh.
Yeah, so, and then in my own, yeah, free time. No, I mean when I was a student, I did it a few times. You know what really makes this problem suck? Is if you did something like this. That little change right there is huge because now you just really start messing up your constants because when you do the antiderivatives, you start getting like 1/5 and then the distribution starts getting massive. Or if you want to just make yourself want to quit life, there you go. Make it 8th power, you know, like that is brutal. That's brutal. Now I would never do that to you. And I think the most the book does is 6th power. And even that in itself is kind of not nice. Yeah. Number 10 is cosine to the 6th.
You're kidding.
I'm not.
I guess there's a reason why some of the professors here don't like the book.
No, I expect that. I expect to see that. Every student should do at least cosine to the 6th or sine to the 6th. Because you see all these little details you have to keep track of? And that's what makes you good at this stuff, you know, because the problems get longer. You take differential equations, right? How many of you have to take Diffie-Q? Anyone have to take, or engineering analysis, right? If you have to do those courses, you're going to be doing problems where one problem you're going to see pre-cal, cal 1, cal 2, you're going to see it all in there. All those little details you have to pay attention to. So this is a good example of a problem that doesn't look that bad in the beginning and just starts to grow and grow and grow. All right. Okay, let's shift gears a little bit. Shift gears. If we had sine to an even power, we would do the same thing, but we use this formula instead, right? Okay. So how about this? Oh, now we've got sines and cosines together.
Yeah. He just said shift gears. He didn't say which way.
Yeah.
It could have been from 2 to 7, or 2 to 6. 6.
All right, so let's see here. Tatum, you're up. We haven't even done one of these, Tatum, so yes.
Can we take the derivative of that and then check it if we wanted to?
Yes. The answer we just got? Yeah, if you take the derivative of it, you should get back cosine to the 6th x. There's going to be quite a few identities that will be required to get you there, but yes. Yep. If you type that problem into Wolfram Alpha, let's do it real quick. I can almost assure you their answer is not going to look like ours. Okay, so if I do integrate, oops, Grateful Dead. Integrate cosine x raised to the, it was 6th, right?
Yeah. You gotta blow up your computer.
There it is. So that's the answer they got. Now, 60 over 92 probably reduces. What was our number? What did we have in front of x? What was it? 5/16. So yeah, that should work, right? So we got that right. Okay. Now, do we have a sine 2x? We have a sine 4x? We don't have a sine 6x, do we? We have sine cubed. So what Wolfram alpha has done is it's gone ahead and anywhere where it had squareds or cubes, it's used reduction formulas to take those down to all, basically, yeah, single powers on all their trig functions. That's just the algorithm built in. That's the way they designed it. But we stopped, right? We got to cosine cubed. We were like, at the end, we're like, there it is. There's the antiderivative. They're the same answer. They just look different, right? So I always can tell, like, on a student who like types this into a TI-89 or TI-Nspire CAS on a test, right? Because they'll get an answer that no way in the world they would have gotten. No way. Just no way. Because the computer is going to simplify beyond what you would do, right?
That's why in the workplace they don't let you do calculus by hand anymore.
They don't in the workplace. They don't.
In general,
Really?
usually you can do that like to start off, but you have to double check it with the computer.
Hmm.
You know.
All right. So what about this one? Tatum almost got off the hook. Almost got off the hook, Tatum. So I haven't given you an example of this, right? All right. So using what we just talked about, we did this when we had odd powers of sine and cosine, right? And we used these when we had even powers of sine and cosine. Here, we have both scenarios at one time, right? But just let's start with the idea of substitution. Is there something you could peel off? A sine? Okay, so let's see. If I peel a sine off, I'm left with sine squared x, cosine squared x, sine x dx. Okay. So Tatum, if we do that, then I'm guessing that sine x dx is the derivative, right? That's the derivative part. So that means you need your u to be a what? Cosine, right? That's what we said? So if this is going to be the derivative of cosine right here, then I need cosines over here, don't I? Do I have cosine here? There I do, right? Sine squared is not cosine, but sine squared is 1 minus cosine squared x. So you could rewrite this as 1 minus cosine squared x, right? Cosine squared x, sine x dx, right? That's the same thing. And now make your substitution. Yes?
I just have a question.
Yes?
I broke the integral apart, so I did like integral 1 minus cosine squared x times sine x times integral cosine squared x, and then I just used both different ways to do each part.
Wait a minute. So you broke it apart. I'm not sure what you mean. So like you distributed that here and then broke it into two? No.
So I took the sine cubed x and I put integral sine cubed x times integral cosine squared x.
Oh.
And each different. Is that?
Oh, like this. And then a separate integral?
Then a separate integral.
All right. Well,
I just did
I'm gonna let you answer the question. Can you do this? Okay, so let me ask you this. Do you recognize that as something we would use integration by parts on? Right? Why not just do this? That would have been easier, right? It's because we can't do that with integrals. So it's the same reason in Cal 1 that the derivative of a product is not just the derivative of each one multiplied. We have the product rule. The antiderivative of a product, is not just the product of the antiderivatives. Or else Cal 2 would be much easier class, much easier class, right? If you just had to, you'd always just split them up, and it would be. I mean, it would be much different. So we don't have that choice. All right. What now? U substitution. What's U? U's cosine x. What's du? Negative sine x. But I don't want a negative sine x. So I'm going to put the negative on this side. right? And now we can rewrite the problem. This becomes, Ricardo? Yes. Okay, so what is this new integral in terms of u?
1 minus u squared.
1 minus u squared times u squared du and a negative, so I'll put the negative out there. Now how could you handle that? Just distribute, just pass the u squared through, right, like that. And I'm going to put the negative back in, only because this is going to become like u squared minus u to the fourth, right? If I put the negative back in, then I can rewrite it as u to the fourth minus u squared. So kind of flip them. And that we can do with just power rule. And then replace your u with cosine x, and we'd be done.
-1 at the other.
Well, I distributed this u through, right? That became u squared.
Right.
And this became negative u to the fourth. And then I pushed the negative back through and flopped them.
So wouldn't the first term be negative then?
It is. I switched these. So that u squared became negative u squared. You didn't have to do that. I just did it that way. All right, so that one worked, right? That kind of worked out? Okay. So what could possibly cause an issue here? Like, it seems like if one of these is odd, right, and the other one's even, we should be able to peel one off? What if they're what? What if they're both odd? Let's make that cosine to the fifth. We haven't even started working with tangents and secants yet. We're just sticking with sines and cosines right now, right? We've got a lot of other trig functions to talk about. And don't we, in fact, have 3 other identities, Pythagoreans? Yep. We have something with with tangents and secants and cotangents and cosecants. So we are unfortunately not going to get through this whole section today, which is not good. But it's okay, because we have, I'm trying to stay a little ahead. Are we? We're a little ahead. Remember, I've said any time, additional time that we can get, you will be happy about later. Okay, so you can peel something off? What do you want to peel?
You just peel off the sign again.
You want to peel a sign off? I'm okay with that. Let's see what happens here. Sine squared x cosine to the fifth x. You peel the sine x off, right? Like that?
Yeah, and then
Okay.
you can still use the identity 1 minus sine squared, or sorry, 1 minus cosine squared for the sine squared.
Yeah, this will still be a 1 minus cosine squared.
Yeah, and then you still use cosine as your u.
Yep,
And it's just the same thing, it's just that last u has a higher power.
that's right. Cosine to the fifth x sine x dx. So this will still work. If u is cosine x, this will become 1 minus u squared times u to the fifth, right? And then negative du or whatever. But we should still be able to do this. This should be all right. No problems. So if one of them is odd, the other one's even, we seem to be good. If they're both odd, seems to be reasonable that we can get it. What if they're both even? We go drop the class. What if they're both even? Ugh. Yeah, I mean, why don't we just use... Oh, wait, the what?
The double angle formula with like sine of 2x equals 2 sine x cosine x,
So-
right?
Oh, I see. Okay, I see what you're saying.
Sine of cosine x, you could just reduce it to like
That's
sine to a single power, and then just do it how we did.
I thought for the double angle you had to have a constant with x.
I see what you're saying. You're saying...
You just have like,
Well, I think I see what you're saying. Double angle formula.
yeah. Like the
So
first
which-
one under double angle formula, that
The sine of 2x? That one?
where it says like sine of 2x, yeah, is like just sine times cosine. It's 2 sine times cosine.
Yeah, I'm just trying to see, what do you mean by using this one?
So like if we have sine times cosine times cosine, could we
Mm-hmm.
kind of convert it that way?
You could, but you still have a bunch of products, right? It's still a bunch of stuff multiplied.
So eventually though, it'd just be like sine to a power, there'd be no cosine. Right? Because for every sine we have a cosine, so all of those just become sine to a power of sine of 2x. So you have like sine squared of x plus like sine squared of 2x times.
I'm not going to say no to what you're saying. I'm thinking it might work. I'm thinking it might be a little bit kind of the longer path, but I think what you're saying is make this, like that. Is that what you're saying? Or no? I'm just trying to see how you want me to use this formula.
So like if you break it out so there's like, you match everything up. So you have like sine squared and cosine squared. So it's like sine, cosine, sine, cosine.
Oh, okay. I see what you're saying. I think, well, I see what you're saying.
Sine squared. Yeah.
Yes? Okay.
You have a sine squared on the end. And those first
Okay.
two groups would just become, you know, more sine 2x. Yeah.
Yes. Okay, and then this last one,
Just, yeah.
that formula over there? Yeah, because you have two x's here. You have two x's here now,
Yeah.
right? So you need two x's. So now you're going to have a cosine in there. Yeah, it probably work. I think that would work. Yeah, that'd work. So more than one way to get to this. That looks like it would work. I'm going to try something different though. So something we're going to run out of time. We can't peel a single cosine off, right? Or sine. Because let's say we peel a cosine off. Then we're going to have cosine to the first power, and we don't have a way of converting that to a sine. What if we peel a sine off? We're going to have sine cubed, and we don't have a way of converting that to cosine. So what you could do is take this one right here, that's sine squared x squared, and then this is cosine squared x, right? Dx. Rewrite sine squared using the 1/2 1 minus cosine 2x. That thing squared, right? Times, what's this? Using that over there. 1/2 1 plus cosine 2x. Do y'all see I'm using the power reducing on both of those? So I'm power reducing this one, power reducing that one, but that one's squared. So now this becomes 1/4 1 minus cosine 2x, that quantity squared, times 1/2 1 plus cosine 2x dx. Yes?
What's the difference between the sine squared x on the top and the bottom one?
Minus and plus.
No, I mean sine squared x and then there's one on top. You know, like there's the sine squared x, that one, and then there's one on the bottom.
Oh, there's a big difference between these, right? This one gives you a relationship between sine squared x and cosine squared x. This one gives you a relationship between sine squared x and cosine 2x, not squared. Yeah. Okay, I'm out of time. But do you see what you could do here now? Expand that. Take all your constants out. Expand that, and then multiply it times this. And then look at each of those and see how to go about those. It might be odd powers, might be even powers. It'd be messy. All right, so for your homework, you can start 6.2, but you're not going to make it very far. 1 through 61. I'm asking you to do the first 61 problems here. That's a lot of work. I would say you're probably only safe to venture out to the first 16 problems. 1 through 16. And even on some of those, a little messy. All right, everyone. Remember, tomorrow, no office hours in the morning. Friday, I won't be here. Yes.